Now we're going to show what Centroid has some very powerful tools that can be used for creating custom PLC programs as well as troubleshooting things out in the field. Alright. We'll open up the Centroid software. First and foremost is our PLC Diagnostic Menu. Okay. At the main screen, if you press Alt and the letter I, that will bring up our PLC Diagnostic Menu. Ever since CNC 10, we have added this menu on there. Now, granted, on older systems, you might only see 3, but typically newer systems, you will see 4 rows. The top row will always be your inputs. The row directly underneath that are outputs. Then underneath that, we have memory bits. And then underneath that, we have stages. And if you take a look underneath all those 4 rows, right in the center of the screen, will give you the nomenclature of what that particular item is defined as. And that item is highlighted by this white box. And currently it's on input 1, and it says input 1, and we have the PLC program has that defined as AX1 underscore minus limit OK, which of course, that is your first axis limit switch. Right. Underneath the definition, we have some word values that you can end up scrolling through and seeing that are being utilized in the PLC program. And of course, there's some timers built into that. No one's really going to actually end up using that or needing these timers on the bottom. But if anything, you might be looking at certain word values. And as you can see here, this page shows 80 of them. As you can see, it goes from 1 through 9. Then it's got a 0 and a number on top. The number on top tells you what 10th it is. So of course the 1 and the 0 means that that is item number 10. Then we go 1 through 9 again. So these are 11 through 19. And then there's another 0 with the 2 on top. So that's number 20. Okay. So this page, like I said, shows the first 80. Now granted, we have almost 1,300 inputs that you can end up seeing. But of course, you're only seeing 80 of them at this point in time. That's where you have these previous page and next page, F12 and F11 keys. If you hit that, that'll take you to the next bank of 80. And of course, it goes from 81 all the way up to 90. And that continues on up to like 160. And as you can see here, it goes from word 11 all the way up to word 20. And you keep scrolling down until you get all the way. As you can see, we no longer have any more stages and no more memory bits. That's because our memory bits stop at 1024. And so there aren't any more. The other thing too, you can see here, now we started looking into DWs, which the DW is a double word. The double word is that 64 bits word value. And you can keep continuing on until you get stuck at your limits on your I/O, which is 1312 on both inputs and outputs. Okay, so let's just go all the way back to the beginning again. Oops. All right, and for the most part, the majority of people, you'll be using the first bank of 80. Now, of course, you can definitely use a lot more because depending on what you're connecting to, like let's say you're looking at signals going from your probe connector or your MPG connector. Those are mapped to higher inputs than the 80, so you would just scroll through, and if you wanted to check to make sure that something was turning on and off. Okay. As of right now, you'll see that you have either a red or a green dot. The red means false state. The green means true. Now, it does not mean open and closed because we have the ability of inverting an input. So for example, just wanted to mention that by default, all our inputs are basically veered as normally closed. So we're looking to see that a closed input is in its true state. All right. So right now, inputs 1 through 6 are closed, 7 and 8 are open. But of course, if I just flip the switch here, you can see my input is changing state, and it's going from an open right now to a closed state. Okay. But now I also mentioned that one has the ability to invert an input. So let's say you have something that's wired on there and it's not normally closed, it's normally open. Let's, for instance, say that input number 7 is a normally open input. So what we would do is just use the arrow keys to move that white box, highlight that over the particular input, and now hit Control Alt and the letter I. All right, it's the same thing as Alt I brought the PLC diagnostic up. Control Alt and I will invert an input, and as you can see, the color of that input went from red to green, and there's a white line above that input. Let me just move that over. Now you can visually see that white line. That white line tells the control that that particular input has been inverted. So the input, I didn't physically switch it. I just inverted it, which means that the input is in an open state. But in the PLC diagnostic, that green means that that is in a true state. So if I closed that input now, you can see that that goes red. And if I go back and invert it again, just by doing Control Alt I, it's now in a closed state and it goes green, because when it was closed, it's now green. Okay, let me open that switch up again. All right, so one can easily invert an input just by moving it over or highlighting that particular input and issuing the Control Alt and I. Now another good thing that we can end up doing is forcing outputs. All right. Now to force an output, you would do something very similar. You just move over. All right. Well, for example, we'll just go on this one. This one on here, in the particular PLC program, it's defined output 7 as the spindle enable out. All right. And right now it's red, which means it's not on. And of course, because we didn't tell the thing to turn on. Let me see if I can go ahead and reset it. Let me go ahead and turn that spindle on. And you can see now I commanded the spindle to turn on. That output went green. I tell it to turn off. That output turned off. All right. I don't know if you can hear the relay clicking, but if you can, it clicks on. Well, you'll hear it clicking either on and off as I turn it on and off. But if I wanted to force that output on, I can go in here, highlight that particular output, and hit Control Alt and the letter F for forcing. And you can see that that output went from red to green, which means that it's now on. The relay turned on, and there's a white line underneath it. That white line underneath tells the system that that particular output has been in a forced state. Okay. Now, you can force an output on, and you can also force it off. So by doing Control Alt F again, it's now off, but if you take a look, that white line is still there, which means that it's in a forced off state. If I do it Control Alt F again, that'll take me back to the original state, which means that the PLC program will control it. Okay. This is very important because I've actually had a few calls where people had told me that certain things weren't turned on. And then when we team viewered in, what I found out was that, yeah, someone went in there and actually forced that particular output in the off state. So even though they were trying to do things in the PLC program to actually be able to turn it on, because it was a forced off state, it was never physically turning on. Or, yeah, never physically turning on. Okay, so remember, in forcing, first one forces on, second one forces off, and then the third time brings it back to normal. All right, so I'm just going to go ahead and force this on, and now I'm going to go, and you can see that when I'm trying to click on the virtual control panel here to turn that spindle off, it's not turning off. That's because it's in a forced on state. Now if I hit Control Alt F again, I force it off. If I try to turn it on, as you can see, it's not coming on because it's in that forced state. But if I do it Control Alt F again, that white line goes away from there. You no longer see it. Now when I try to turn it on, I can turn it on and off using the PLC program. Okay. This is also very helpful because a lot of times if you're trying to find something or verify whether something isn't being turned on, or to see if it might be an issue with your wiring, you can easily go in here into the PLC program, force an output on, and verify that you're wiring everything inside the electrical cabinet is working correctly. So that right there is the one item, which is the PLC Diagnostic Menu. Remember, this has to be on the main page, and you just hit Alt-I to turn it on, and then Alt-I again will turn it off. Alt-I, turn it on. Alt-I, turn it off. Okay? Another big, powerful tool is PLC Detective. All right? With that one, when you're at the main screen, you're going to hit Control and the letter E. Okay, when PLC Detective is up, this will actually show you your actual source code file. All right? And this is a very powerful tool, like as I was saying. Pretty much whenever you're going through and troubleshooting, it gives you the states of various different inputs, memory bits. It can even give you word values on there that you can use for troubleshooting. Let's go down to the actual logic here. For example, on here, let's just say on whenever something is in a true state, or if it's being set, it will be highlighted in blue. Like we were seeing on this line of logic that says, if not using feed rate knob underscore M and not jog overlay underscore M. Well, as of right now, this entire condition is highlighted, which means that this condition is true. But then that means that the using feed rate knob underscore M is not being set. And because that there is that not symbol in front of it, it means that as long as it's not being set, it makes that part true. And if we take a look, I don't know if you've been noticing, but if I move my mouse over, I end up, if I hover over a word value, it tells me what that value of that particular word is. Pretty much any word value that's on there, it'll associate or give me that. The only thing that this does not allow you to do is, like, let's say you're hovering over the SV machine parameter 39. Even though the machine parameter 39 is a system variable and it's the value of parameter 39, we can't see what value it is. Unfortunately, you can't see anything with system variables. But if you were to copy that system variable and put it into a word, then you can see that word value. Okay. All right. So then we go in, and like I said, this allows you to actually, when you're going in and troubleshooting, you can see what part of the condition is being set to determine why your outcome is not turning on. So, for example, if I had it to where this one was not set, but this one was set, then it would tell me, if I was looking at it and figuring out, all right, well, why is final feed rate override word value not the same as my keyboard override word value? And if I look on here, I can say, oh, it's because this memory bit was not being set, so that explains that. All right, let's keep trying to see if I can find another good, decent example here. And that's my axis. Okay, here's one. All right, on here there's essentially 3 conditions that need to be met in order to throw this or in order to perform this outcome. And as you can see, the outcome isn't being set or isn't being turned on. But in order to make that outcome turn on, this initialized timer is the one condition, and we see that that's in a true state. We see that this not lube OK is not being set, which means that that's not in a true state, and this not SV program running is not being set, or I'm sorry, is being set, so it's in a true state. So that means that based on this, the reason why this is not being set is because this one part of this is not being set, or this condition is not being met. Now, if I needed to find or figure out what that lube OK is, I could see whether or not that's an input. That could be a memory bit. Could be a timer. That's why the majority of the stuff that we like to do is that we like to put in, like if it was a memory bit, an _M, or if it was a timer, we'd put an _T. I know in the near future we're going to have it to where even our inputs and outputs would have like an _I, so like that you can easily see that that particular definition is an input. If it had an _O, it would be an output, and so on. But I can see that this is my lube OK, and that is pretty much just, I know from experience that that's my lube input. And as you can see, I just flip that input into the open state, and so now that condition got set, and because all those parts of the conditions are all true, now it was able to set this message or set this memory bit, and if I hover over this, I can see that this word value is 6657. And if I go back, I'll see that that coincides with my lube fault. And if you take a look, lo and behold, the CNC software displayed a lube fault message. Okay. So if you were ever getting a message or didn't know why you're getting it, basically you can go in here, see what's being set, and determine the condition that's setting that particular item. And once you know the condition, then you know where you need to go back or try to find to figure out what issue or the condition that it's causing that state. The majority of times it could be where it's a memory bit that isn't being set or is being reset for whatever reason, or it could be tied to a particular input. And if it's tied to an input, then that just means that the control is seeing that the input's in the wrong state. The majority of times it could be either an issue with the switch or possibly the cabling. There was a broken wire or something, it would cause that message. But this is a great thing, a great tool that you can use that says, hey, all right, well, is that thing being set? If not, okay, what can I find out to determine what's actually setting that particular condition? And then that's when you would look at the condition and say, okay, well, in this one, let me just flip it back. All right. Well, as you can see, the input flipped back, but this is still in a set state. Well, that's because this lube fault is setting the thing into a fault state. Your fault states will always remain in a fault state until you cycle the e-stop. So let me go ahead and cycle the e-stop, which clears all the faults, and that is no longer on there. And as you can see here too, we've got that message cleared, and then we've gone ahead and cycled the e-stop to clear all the messages, and then we've released it. Okay, so PLC Detective is a very powerful tool, and like I said, you could use it to figure out why certain things are coming on. Like for example, let's say someone calls up and says that your spindle enable is not being turned on, and you can find out why it's not being turned on using PLC Detective. You go into that output, look at the conditions that it's using to turn that output on, and then one of those conditions is not going to be in the correct state, and then you just have to keep searching to determine, and you'll finally get down to where it's looking at a particular input or a memory bit, which is preventing that output from turning on. That's as long as the software, you see that the software is not turning the thing on. Because the majority of times, if you go and let's say your spindle enable output, let's say you come up here and you're doing the PLC diagnostic and someone says, my spindle isn't turning on. First thing I always do is go into the PLC diagnostic, move over to your whatever output you're asking about, and in this case, the spindle enable out, and go ahead and try to see if the software turns the thing on. If you see the software turning it on, then that means that the PLC program it's seeing everything in the good state, and it's actually physically trying to turn it on. So if it sees it turning on here, then that means that this problem is not a software problem, it's more of a hardware. Now it could be something where perhaps the relay isn't in fact turning on, or maybe there's a fuse associated with it, got broken or blown. Maybe there's a broken wire in the system, or maybe there's if it's controlling a solenoid, maybe perhaps the solenoid is going bad. And at that point, you would have to follow the schematic and use a meter and verify that you're getting the appropriate voltage to that particular item. But at least this way, we see whether or not the software is doing it. And if the software is in fact telling it to turn on and off, then that means that everything that it sees is happy. But if it's not, then you would use something like the PLC Detective to figure out why the software isn't trying to turn the thing on. Another thing too that we can end up doing on here is that we've got this logic analyzer. We can use this logic analyzer to actually check out the states of various different inputs and stages, memory bits, and stuff like that, and see what it's doing. For example, let's see if I can find. Let me do the switch 16. Had 13. Let me take a look here at the logic and see what exactly. OT6. All right, M13. Let's go ahead and look at the timer. OT6 and other fault. Output, timer. Let's just look at other fault. All right, so I'm going to look at these three items. So I'm going to look at the switch in 16, that M13 macro, the output, which is OT6, timer, which is that OT6 underscore T, and the other memory bit that says other fault down. All right. So on here, I am going to trigger off of one of them, and I'm going to trigger off the M13 because I'm going to say, all right, I'm going to start that timer, and it should look at the input switch 16. If everything's good, then it's going to turn off that OT6. All right, and of course, if that timer expires and switch 16 is not in the correct state, then it's going to fault out. So I'm going to go ahead, switch that, triggering off that M13. So whenever M13 gets activated, I'm going to start counting or looking at it from there. I typically like to put a pre-post of, let's say, 5, and post I do 50. Now, depending on what you're going to be looking at, 50 might, well, in this case, 50 is probably going to be a little excessive, but if you were looking at something, for example, for a tool changer, where there's a lot of various different sequences as your things keep changing, you might want to bump that up to 100 or 200 in order to get a clear picture of what's going on. Now, of course, the other thing, too, is that right now, this is going on time-based. I don't want this to be on time. I want this to be on events. So it's going to keep a track of any time any one of those events changes state. So I'm going to go ahead, click to events. All right. And this is rising edge because my M13 is currently not being active. Once I go in there, it will become active. So it's going to go from a low to a high. And yeah, that's pretty much it. So I'm going to go ahead, click start, come down here, go ahead and issue an M13. All right, flip my switch. Oh, and it timed out. All right, if I go into, I can see that, all right, my M13 got activated. Okay, and once that got activated, the next pass, it turned on the output, and then my timer got set the moment it timed out. Now, if I wanted to, once this thing ended up, once it actually timer expired, then next pass was that it set the memory bit, it turned the fault memory bit on, and then once it turned that memory bit on, then OT6 turned off. Now, of course, you might be looking at this and saying, hey, there was a good amount of time that passed between that, but that's not it. Once again, we are in a event stage. So what ended up happening was that turned on M13. Once I turned M13 on, then OT6 turned on. All right, that timer started. Then the timer expired at this point. Once the timer expired, I set this memory bit, and I also turned off that OT6. And then, as you can see, this was me trying to flip that switch, but I flipped the switch way before the timer ever expired on there. So that's why it didn't turn the thing off, but it turned off because other fault M was being set. Now, another thing you can end up doing on here is if you right click and left click, you can add a timer to see. Doing that. Oh, okay. Alright, looking at there, then moving there, and I can see that the difference between those 2 points right there is roughly 2 seconds, which is that timer that we ended up having. So this output turned on, and then within 2 seconds, that timer got set, and of course, once that timer got set, then we see that this other fault ended up being set. And if you wanted to, we can even take a look from that point to that point. That's only 20 milliseconds. All right, so that's one complete pass of the PLC program. And of course, between that point and that point, it's probably going to be, oops, 20 milliseconds again. So after that other fault got set, then another 20 milliseconds happened, which is one complete pass of the PLC program, and it turned off that output. Okay. So you can definitely see on here that you can end up using this to try to pinpoint and figure out what exactly was going on, why certain things weren't being turned on. The biggest ones that I've seen on using this was for tool changer stuff, where they had various different inputs, and I didn't know what the state of the inputs needed to be for that particular tool changer. So what I did is I'd use this logic analyzer, look at those inputs, and then I'd force the output on that would move the carousel of the tool changer, and just look at the various state of the inputs and figure out, okay, this is how I know when it was at, let's say, for example, tool number 1. I saw that it needed these bits to be set. When it was at tool number 2, it needed those bits to be set. And so on. So this is definitely a very powerful tool that gets used, especially when troubleshooting. Typically, the logic analyzer, don't use it too much on troubleshooting, other than if you're trying to figure out why your custom PLC program isn't working. But on troubleshooting, where someone calls and says that, you know, a particular output isn't turning on, go in here, figure out, all right, why is that output not being on? Look at the conditions, see if a particular condition is being set, and if not, then keep searching back to try to figure out why that condition isn't being set. And typically, you'll end up going as far back as to finding the particular input signal that that condition is looking at.